Okay, here's your second video. So this one's on your physical and chemical change and properties. Physical property is a property that you can observe or measure, and it doesn't change the identity of the substance. So the fact that this ink pad is green would be a physical property because I can observe it, and guess what? It's still an ink pad. Another physical property would be the fact that water boils at 100 degrees. Saying that it boils at 100 degrees is a physical property. So this is something that, is not currently happening. It's not a verb. It's just telling you it could happen without changing the actual substance. You have intensive physical properties. Intensive properties are independent on the amount of mass, so it's not going to change. The color of a piece of paper, so in class, I took a piece of paper, it's green, I ripped it in half, so I changed the amount of matter present. Well, the color didn't change, the texture didn't change, and then the density is not going to change either, even though paper is a bad example for that. You did see the fact that the density didn't change in your lab that you did, or you should have seen that. What did change is the volume, the mass, the shape, along with some other things. So you just kind of think, if I take whatever this is and I break it in half, will the property change? If it does not change, it is intensive. If it does change, it is extensive. For a physical change, then it's something that it is occurring, but is not changing the physical makeup. So I ripped this piece of paper in half. The actual process of ripping it is a physical change because I was currently doing it. If I'm boiling water, that is physical change because all I'm doing is changing it from liquid to a gas, but it is still H2O. So that's going to be your physical change. A chemical property is something that you observe or measure, and it does change the chemical makeup. Okay, so the fact that something is flammable. Isopropyl alcohol, rubbing alcohol is flammable. I'm not saying that it's on fire. If it was on fire, it's burning. That's a change. But the fact that it could burn, the fact that it's flammable, that's a chemical property. I'm saying a precipitate will form. That's a chemical property. Saying a precipitate is forming is a chemical change. So you just kind of have to worry about the wording on those when it comes to examples. I could use a lot of examples, but you got to think through the process of it. Okay, the next thing that we learned was the history of the periodic table. We learned about Mendeleev. I'm going to do a lot of talking and not a lot of writing. And we talked about Moseley. So if you remember, Mendeleev is considered to be the father of the periodic table because he was not the first one to come up with the periodic table. There were plenty before him. But what he did that was so unique was that he not only arranged it by mass, but the biggest thing is he left gaps in the periodic table in which he accurately predicted elements that had not been discovered yet. But he knew that there was an element that should go in this spot and it has, XYZ properties. So that's why he's so famous. Moseley then takes the credit because between Mendeleev and Moseley, between the time frame between these two guys, protons had been discovered. And Moseley was like, hey, there's some things not working out with Mendeleev's, so let's try protons. And they arranged it by the atomic number, and voila, we have our periodic table today that we keep adding to all the time. So that's your history of the periodic table. And then we talked about the history of the atom. Again, I'm going to do a whole lot of talking, not a lot of writing. We have Dalton. He had the billiard ball model, it's just a sphere. You think you're playing pool, the balls that you're hitting are the billiard balls. So he thought that the atom was the smallest thing possible, that you couldn't break it. He thought a second postulate, he thought all elements that are the same are exactly the same, which we know is not true anymore because you can change your neutrons and your electrons like we learned with isotopes. He thought that different elements are different. Well, that's great. That makes sense. Carbon's not the same thing as nitrogen. He thought elements combine in whole number ratios to make compounds like H2O, C6H12, O6, like NaCl. there's no 0.5s down here. There's no decimals. It is whole number ratios. So that's true today. And he believed that elements get rearranged during chemical reactions, which is true. We just haven't gotten to that yet. And then you have Thomson. Thomson discovered the electrons and that they were negative. He did that with the cathode ray tube. And he came up with what's called the plum pudding or the chocolate chip cookie model. So the dough is positive and all the little chocolate chips are negative. His next one was Rutherford. Rutherford discovered the nucleus. He discovered it was positive and very dense and surrounded by mostly empty space. He did that with the gold foil experiment. Remember, you guys got to throw alpha particles at the nucleus that I was holding in front of me. So it's called the gold foil experiment. There's some great videos on YouTube about that if you're interested. The next one is Bohr. Bohr discovered energy levels. He thought electrons rotated around the nucleus like Earth rotates around the sun. Chadwick, he discovered the neutrons. And then Schrodinger discovered that Bohr wasn't correct and that they're not even orbits, but instead they're electron clouds. He did a lot more, but I'm simplifying this. And the Bohr model, by the way, had a nucleus and then, those energy levels around it. Again, look at your notes for this, and my notes are posted on Canvas with that card sort that we did as well, so that could help. The next thing was isotopic notation and knowing protons, neutrons, and electrons. So again, a lot of talking, not a lot of writing. Protons, neutrons, electrons. These are positive, located in the nucleus, have a mass of 1 AMU. Neutral, inside the nucleus, has a mass of 1 AMU. Negative, outside the nucleus, relative mass is 0, so we don't consider it when we're worrying about the mass. You need to remember that mass number is equal to protons plus neutrons. To get your charge, it's protons minus electrons, and that atomic number is the same thing as your number of protons. Key things, you gotta know it. Your isotopic notation looks like this. So for this particular one, there are 6 protons. My mass number is 13. There's no charge, and my symbol is carbon. From this, you can identify your protons, your electrons, and your neutrons. Well, since the bottom number is 6, I have 6 protons. Since there's no charge, I have 6 electrons, because 6 minus 6 would give me 0, and there's a 0 charge. Okay, neutrons, how you figure that out is you take your mass number and you plug it into this equation. Mass number is 13, protons is 6, 6 plus some number gives me 13. That's going to be 7. So that's how you get it from that. And then you have your hyphen isotopic notation where you take the name, carbon, hyphen, the mass number. So this is where it's important that you still know your elements. All right, as far as your test, this is a brief review. Make sure you study your notes, look on Canvas. There's some great videos there. There's some great practice. But look there for all of that information and keep studying all that. We have one more topic to learn, which is your average atomic mass. And we'll do that next class. Some of y'all may not watch this video until after next class, so you're not going to have a review portion on that. So make sure you review your notes for that portion. All right, that's it.